Tonight, we're going back further than any human story, further than any mountain or ocean, back to a time when there was no time, when there was no space, when there was quite literally nothing at all. And then, in the smallest fraction of a second you could possibly imagine, everything began. If this kind of deep, slow journey through cosmic history helps you unwind, feel free to like the video and subscribe, but only if it actually brings you peace. And let me know in the comments where you're listening from and what time it is right now. There's something strangely comforting about knowing we're all here together, drifting through the same infinite darkness, pondering the same impossible questions. So dim the lights, maybe turn on that soft background hum if you like it. Settle in, and let's begin at the very beginning. Not the beginning of life, not the beginning of Earth, not even the beginning of stars, the beginning of existence itself. 13.787 billion years ago, give or take 20 million years, something happened that defies every intuition we have about how things work. There was no explosion, no bang, no moment when something burst into something else. There was no space for anything to explode into. There was no time for any event to occur within. And yet somehow, from this state of absolute nothingness, everything that has ever existed began to unfold. Picture this if you can. You're floating in perfect darkness, perfect silence, perfect emptiness. But not the emptiness of space between stars, because even that emptiness contains something. Particles popping in and out of existence, radiation from distant galaxies, the faint whisper of gravity from massive objects light years away. No, this is different. This is the absence of everything. No particles, no energy, no dimensions, no up or down, no before or after. This is what cosmologists call the initial singularity, though calling it anything feels almost wrong, because there was no thing there to name. And then, in an instant that wasn't really an instant because time didn't exist yet, the universe began. Not with a bang, but with an expansion. Not an expansion into space, but an expansion of space itself. Every point that would ever exist, every location where a star would one day burn or a planet would one day form, all of it compressed into something smaller than the smallest thing you've ever imagined. The first fraction of a second was unlike anything that has happened since. In the first tiny sliver of time, something called cosmic inflation occurred. Space itself expanded faster than the speed of light, doubling in size, then doubling again, then doubling again. Billions upon billions of times in less time than it takes light to travel the width of a proton. This isn't science fiction. This is what the evidence suggests actually happened. The universe went from smaller than an atom to larger than a grapefruit in about 10 to the negative 32 seconds. During this period of inflation, quantum fluctuations, tiny random variations in energy, were stretched across vast distances. These microscopic imperfections would become incredibly important later. They were like seeds, the first hints of structure in an otherwise perfectly smooth cosmos. Without these quantum hiccups, the universe would have remained forever uniform, a bland soup with no galaxies, no stars, no planets, no us. When inflation ended, all that energy driving the expansion had to go somewhere. And this is where things get interesting. The energy transformed into matter and radiation, flooding the newborn universe with the raw materials for everything that would ever exist. The temperature was unimaginable, around 10 billion degrees Celsius. At this point, the universe was about 1 second old. This early cosmos was nothing like the cold, dark space we see when we look up at the night sky. It was a roiling, chaotic plasma of fundamental particles, protons and neutrons and electrons, all moving at incredible speeds, colliding and combining and separating in an endless dance of creation and destruction. The entire universe was smaller than our solar system, but contained all the matter that would eventually form hundreds of billions of galaxies. For the next few minutes, something remarkable happened. The temperature was just right, not too hot and not too cool, for protons and neutrons to stick together and form the nuclei of the lightest elements. This period, called Big Bang nucleosynthesis, lasted only about 20 minutes. But in that brief window, the universe created most of the hydrogen and helium that still exists today. Every helium atom in your body, in the air you breathe, in the sun that warms your face, was forged in those first 20 minutes of cosmic history. But even after nuclei formed, the universe was still too hot for complete atoms to exist. Electrons zipped around freely, creating a kind of cosmic fog that scattered light in every direction. The universe was opaque, like being inside a cloud. Photons, particles of light, couldn't travel far before bumping into a free electron and bouncing off in a random direction. If you could somehow have been there with eyes to see, you wouldn't have seen anything at all. Just a bright, uniform glow in every direction. This state lasted for hundreds of thousands of years. The universe continued to expand and cool, but slowly now, without the dramatic inflation of those first moments. Gravity began to work on those quantum fluctuations that had been stretched during inflation, pulling matter together into slightly denser regions. These were the first hints of the cosmic web, the large-scale structure that would eventually organize matter into galaxies and galaxy clusters. Then, about 380,000 years after the beginning, something pivotal occurred. The universe had cooled enough for electrons to finally settle into orbit around atomic nuclei. For the first time, complete atoms formed hydrogen atoms mostly, with their single electron dancing around a single proton, and helium atoms with their two electrons orbiting a nucleus of two protons and typically two neutrons. This event, called recombination, changed everything. With most of the free electrons now bound up in atoms, there were far fewer particles to scatter light. The cosmic fog lifted. The universe became transparent for the first time. Light could suddenly travel across vast distances without being absorbed or scattered. The cosmos had cleared its throat and found its voice. The light from this moment, the afterglow of recombination, still fills the universe today. We call it the cosmic microwave background radiation, and it's one of the most important pieces of evidence for the Big Bang theory. When radio astronomers Arno Penzias and Robert Wilson first detected it in 1964, they thought it was just noise from pigeon droppings on their antenna. They even tried cleaning off the bird's mess. But the signal remained. What they had stumbled upon was the oldest light in the universe, a baby picture of the cosmos when it was just 380,000 years old. This cosmic microwave background is remarkably uniform, with tiny temperature variations of only about 1 part in 100,000. But those tiny variations map perfectly onto the quantum fluctuations from the inflationary period. The slightly warmer spots correspond to regions that were slightly denser, places where matter was already beginning to clump together under the influence of gravity. These temperature maps are like fossils, preserving the imprint of processes that happened in the first fraction of a second after the universe began. After recombination, the universe entered a period astronomers call the Dark Ages. This wasn't darkness in the sense of evil or emptiness, but literal darkness. The cosmic microwave background had stretched and cooled as the universe expanded, shifting from visible light to longer wavelengths that human eyes can't see. There were no stars yet to light up the cosmos, no galaxies to spiral through space, no black holes to warp space-time around them. Just vast clouds of hydrogen and helium atoms drifting in the expanding darkness. But this darkness wasn't uniform. Those tiny density variations preserved in the cosmic microwave background began to grow. Regions that were slightly denser than average attracted more matter through gravity. As these clumps grew more massive, they pulled in even more material. Over millions of years, What started as microscopic quantum fluctuations grew into massive clouds of gas hundreds of light years across. Gravity is patient but relentless. It worked slowly but steadily, pulling matter together despite the expansion of space trying to spread everything apart. The densest regions continued to contract, and as they did, they heated up. When you compress gas, it gets warmer, just like when you pump air into a bicycle tire and the pump gets hot. These collapsing gas clouds grew hotter and denser at their centers, creating the conditions for something extraordinary. About 200 million years after the Big Bang, the first stars ignited. These weren't stars like our sun, comfortable middle-aged objects that burn steadily for billions of years. The first generation of stars were monsters, some of them 300 times more massive than our sun, and millions of times brighter. They burned fast and hot, consuming their fuel in just a few million years before exploding in catastrophic supernovas that briefly outshone entire galaxies. These first stars changed everything. They were the universe's first fusion reactors, taking the simple hydrogen and helium created in the Big Bang and forging them into heavier elements. Carbon, oxygen, silicon, iron, all the elements essential for rocky planets and living things, were created in the nuclear furnaces at the hearts of these ancient giants. When they died, they scattered these new elements across space, seeding the cosmos with the raw materials for a richer, more complex future. The death of the first stars also created something else entirely. When the most massive stars collapsed, they didn't just explode. Their cores imploded to create the universe's first black holes, regions of space-time so warped that not even light can escape. These primordial black holes became the seeds around which the first galaxies would form, though exactly how this process worked remains one of the great mysteries of cosmology. Recent observations from the James Webb Space Telescope have revealed something startling about these early times. Galaxies that formed just a few 100 million years after the Big Bang appear to be far more massive and organized than our theories predicted. Some of them already contain supermassive black holes, hundreds of millions of times more massive than our Sun. This has forced astronomers to reconsider how quickly cosmic structure could assemble in the young universe. These discoveries remind us that even our best theories about cosmic origins are still works in progress. The universe has a way of surprising us, of revealing new layers of complexity just when we think we're beginning to understand. Every new observation, every deeper look into space and time brings new questions alongside new answers. The story of the universe's first few 100 million years is really a story about the triumph of structure over chaos, of complexity emerging from simplicity. It's the tale of how quantum fluctuations smaller than atoms grew to become galaxies, larger than we can easily comprehend. It's about how the universe learned to make stars, and how those stars learned to make the elements that would one day become planets, oceans, and life itself. But this is just the beginning of the story. The universe was still young, still finding its rhythm. The great cosmic web was starting to take shape, with matter flowing along invisible highways of dark matter toward the intersections where galaxies would bloom like flowers in a vast garden. The stage was being set for billions of years of cosmic evolution, for the formation of solar systems and the emergence of worlds where chemistry could become biology, where biology could become consciousness, where consciousness could look back across billions of years and wonder how it all began. As we drift towards sleep tonight, remember that every atom in your body was forged in the heart of a dying star, that every breath you take contains atoms that have been cycling through the cosmos for billions of years. You are not separate from this story. You are part of it, a temporary arrangement of ancient stardust that has learned to contemplate its own origins. The universe began with nothing and became everything, and somehow, against all odds, it became you. The cosmic web that began to take shape in those early epochs was unlike anything we can easily visualize. Imagine the largest structures you know, mountain ranges that stretch across continents, ocean currents that circle the globe, storm systems that span thousands of miles. Now imagine structures millions of times larger, invisible highways of dark matter threading through space like cosmic scaffolding, creating a framework upon which ordinary matter could build cathedrals of light. Dark matter, this mysterious substance that makes up roughly 85% of all matter in the universe, doesn't interact with light or ordinary matter in ways we can easily detect. It doesn't glow, doesn't absorb light, doesn't even bump into itself the way normal particles do. Yet without it, the universe as we know it could never have formed. Dark matter was there from the beginning, clumping together under its own gravity, creating the invisible architecture that would guide the formation of everything visible. As the first stars began to die and scatter their newly forged elements into space, something beautiful started happening. The next generation of stars that formed were different from their ancient predecessors. They incorporated these heavier elements into their structure, becoming smaller, more stable, longer-lived. They could burn for billions of years instead of just millions, creating the steady sources of energy that would prove essential for the complex chemistry of life. Around these second-generation stars, something unprecedented began to occur. The heavier elements they inherited started to condense into solid particles, dust grains no bigger than smoke particles, but carrying within them the potential for worlds. Silicon and oxygen combined to form rocky minerals. Iron atoms clustered together into metallic cores. Carbon began its long journey toward the complex chemistry that would one day animate living things. These dust grains swirled in vast disks around young stars, colliding and sticking together through electrostatic forces and gentle gravitational attraction. Over millions of years, dust became pebbles, pebbles became boulders, boulders became asteroids, and asteroids became planets. The universe had learned to build worlds, but planets were just the beginning. On at least one of these worlds, and likely countless others scattered throughout the cosmos, something extraordinary happened. The chemistry of life emerged from the chemistry of rocks and water and atmosphere. Simple molecules learned to copy themselves, to evolve, to become more complex. Single cells learned to work together. Life learned to harness the energy of starlight and to transform the very composition of planetary atmospheres. This process took billions of years, but it represents perhaps the most remarkable phase transition in cosmic history. The universe had gone from a state where information could only be stored in the quantum fluctuations of empty space, to a state where information could be encoded in the structure of molecules, where molecules could build machines capable of processing that information, where those machines could eventually develop the capacity to understand their own origins. Meanwhile, on the largest scales, the cosmic web continued to evolve. Galaxies grew and merged, their supermassive black holes consuming matter and energy, sometimes quietly, sometimes in brilliant outbursts that could be seen across billions of light years. Dark energy, even more mysterious than dark matter, began to dominate the universe's expansion, accelerating the stretching of space itself and determining the ultimate fate of everything that exists. Recent observations have revealed that this dark energy might not be the constant force we once thought it was. There are hints that it may be changing over time, weakening or strengthening in ways that could reshape our understanding of the universe's future. Some measurements suggest that the expansion of space itself might be accelerating faster now than it was in the past, while others hint at subtle variations that don't fit our current models. These discoveries remind us that the story of cosmic origins is far from over. Every new telescope, every new detector, every new way of observing the universe brings fresh mysteries alongside fresh insights. The James Webb Space Telescope has shown us galaxies that formed earlier and grew faster than we thought possible. Ground-based observatories have detected gravitational waves from colliding black holes, giving us an entirely new way to study cosmic evolution. Underground detectors search for the elusive particles of dark matter, hoping to finally understand what makes up most of the universe's mass. But perhaps the most profound discovery of recent decades is just how much we don't know. Dark matter and dark energy together make up about 95% of the universe, yet we understand almost nothing about what they actually are. We know they exist because of their gravitational effects, because of the way they shape the large-scale structure of the cosmos, but their fundamental nature remains completely mysterious. This might seem frustrating, but it's actually cause for excitement. We live at a time when the universe is still revealing its deepest secrets, when each new observation has the potential to revolutionize our understanding of everything. We're like explorers standing at the edge of a vast unknown continent, with maps that show only the coastline and leave the interior blank, waiting to be filled in. The cosmic microwave background radiation continues to be refined by more sensitive instruments, revealing ever more subtle patterns in the temperature fluctuations that carry information about the universe's first moments. These observations have confirmed many predictions of the Big Bang theory with extraordinary precision. But they've also revealed tensions and inconsistencies that suggest our understanding is still incomplete. Some of these tensions center around the rate at which the universe is expanding. Different methods of measuring this expansion rate give slightly different answers, a discrepancy known as the Hubble tension. This might seem like a minor technical issue, but it could be pointing toward new physics, new understanding of how space and time and matter interact on the larger scales. Other puzzles emerge from the study of the universe's earliest galaxies. How did supermassive black holes grow so large so quickly in the cosmic dawn? How did the first galaxies assemble their stars so efficiently? Why do some of the most distant galaxies appear brighter and more massive than our models predict? Each question opens new avenues of investigation, new possibilities for discovery. The search for life beyond Earth has become intertwined with our understanding of cosmic evolution. We now know that planets are common around other stars, that organic molecules exist throughout space, that the building blocks of life are present wherever we look. The question is no longer whether life could exist elsewhere, but how common it might be, how it might evolve under different conditions, whether intelligence and consciousness are rare accidents or inevitable outcomes of cosmic evolution. As we probe deeper into these mysteries, we're also developing new ways to observe and understand the universe. Gravitational wave detectors can sense ripples in space-time itself, opening up an entirely new window on cosmic events. Neutrino observatories can peer into the hearts of stars and supernovas, detecting particles that carry information from the most extreme environments in the universe. Space-based telescopes can observe wavelengths of light that never reach Earth's surface, revealing hidden aspects of cosmic structure and evolution. Each new discovery adds another piece to the puzzle, but also reveals how much larger the puzzle actually is. The universe keeps surprising us, showing us phenomena we never expected, forcing us to expand our theories and sometimes to abandon them entirely. This is the nature of scientific discovery, the way understanding grows through careful observation and bold speculation, through the willingness to be wrong and to learn from being wrong. The story we're telling ourselves about cosmic origins is constantly evolving, becoming richer and more nuanced with each passing year. We've come to understand that the universe is far stranger and more beautiful than anyone imagined just a few decades ago. It's a place where space itself can expand faster than light, where matter can curve the geometry of space-time, where quantum fluctuations can grow into galaxies, where the vacuum of space seethes with virtual particles popping in and out of existence. And yet, for all its strangeness, the universe follows rules that we can discover and understand. The same laws of physics that govern the falling of an apple also govern the formation of stars. The same quantum mechanics that makes computer chips work also shaped the distribution of matter in the cosmic web. There's a deep unity underlying the apparent complexity, a set of fundamental principles that connect the smallest scales to the largest. This unity suggests something profound about the nature of existence itself. We're not accidental observers of a chaotic universe, but integral parts of a cosmos that has evolved the capacity to understand itself. The atoms in our brains were forged in stellar cores. The molecules in our cells follow the same chemical rules that govern reactions in distant nebulae. The electrical impulses of our thoughts obey the same fundamental forces that light up galaxies. Human consciousness represents something genuinely new in the universe's history, as far as we know. For the first time, matter has organized itself in such a way that it can contemplate its own origins, can ask questions about the meaning and purpose of existence, can feel wonder at the beauty and complexity of the cosmos. This might be happening on countless worlds throughout the universe, or it might be vanishingly rare. Either possibility is profound in its own way. The universe that began with nothing has become capable of understanding itself through us, through minds that arose from billion-year processes of stellar evolution and planetary formation and biological development. We are the universe's way of knowing itself. Temporary arrangements of ancient atoms that have developed the remarkable ability to look back across cosmic time and piece together the story of how everything came to be. Tonight, as you drift towards sleep, you're surrounded by invisible traces of this cosmic story. The cosmic microwave background radiation passes through your body every moment, carrying information from when the universe first became transparent. Neutrinos from the sun stream through you by the billions, particles that began their journey in nuclear reactions 93 million miles away. The very atoms of your body have been recycled through multiple generations of stars, part of an unbroken chain of cosmic evolution, stretching back to the Big Bang itself. You are not separate from the universe. You are the universe becoming aware of itself, a brief flickering of consciousness in the vast darkness. A moment when the cosmos pauses to wonder at its own existence. The story that began with quantum fluctuations in the void has led, through an unimaginably long and complex series of events, to you lying here now, contemplating the mystery of it all. The darkness that followed recombination wasn't empty. It was pregnant with possibility, filled with invisible currents of matter flowing along the scaffolding of dark matter, like rivers finding their way to the sea. For 200 million years, the universe held its breath, waiting for something to break the silence. During this cosmic dawn, gravity worked with infinite patience. The tiny density variations that had been imprinted during inflation, preserved in the cosmic microwave background like fossil fingerprints, slowly grew into something magnificent. What began as differences of 1 part in 100,000 became differences of 1%, then 10%, then regions where matter was twice as dense as the cosmic average. In the deepest wells of this invisible dark matter web, hydrogen and helium gas began to accumulate. These weren't the gentle accumulations we might imagine, but violent processes involving temperatures of millions of degrees and pressures that would crush any known material. As gas fell into these gravitational wells, it heated up, glowing briefly in X-rays before cooling and settling into the growing structures. The first stars that emerged from this process were unlike anything that exists today. They were titans, some containing 300 times as much matter as our sun, burning with the fury of 1,000,000 suns combined. Their surfaces blazed at temperatures of 50,000 degrees, hot enough to ionize the hydrogen around them for hundreds of light years in every direction. These stars lived fast and died young, exhausting their nuclear fuel in just a few million years. But their brief lives had consequences that echo through cosmic time. These stellar giants were the universe's first alchemists, transforming the simple hydrogen and helium of the Big Bang into the periodic table of elements. In their cores, temperatures reached billions of degrees, hot enough to fuse helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Layer by layer, these stars built up the heavy elements that would become the foundation for planets, for life, for consciousness itself. When these massive stars finally exhausted their fuel, they didn't fade away quietly, like smaller stars would billions of years later. Instead, they collapsed catastrophically, their cores imploding in less time than it takes to blink, then rebounding in explosions that briefly outshone entire galaxies. These hypernovas scattered the newly forged elements across vast regions of space, enriching the primordial gas clouds with the raw materials for a more complex cosmic future. But the most dramatic consequence of these stellar deaths was something even more extreme. When the most massive stars collapsed, their cores became so dense that they punched holes in space-time itself, creating the universe's first black holes. These weren't the stellar mass black holes we observe today, but intermediate mass objects containing hundreds or thousands of times the mass of our Sun. Seed black holes that would grow over cosmic time into the supermassive monsters that lurk at the centers of galaxies. Recent observations from the James Webb Space Telescope have revolutionized our understanding of this epoch. Galaxies that formed just 300 million years after the Big Bang already show signs of chemical enrichment that should have taken much longer to develop. Some contain stars that appear to be hundreds of millions of years old, in a universe that was itself only 600 million years old at the time. These discoveries suggest that the first generation of cosmic structure formation happened much more rapidly and efficiently than our models predicted. Even more puzzling, some of these early galaxies already harbor supermassive black holes containing hundreds of millions of solar masses. How such massive objects could form and grow so quickly in the young universe remains one of the great mysteries of modern cosmology. Perhaps black holes formed directly from the collapse of primordial gas clouds, bypassing the stellar phase entirely. Or perhaps the first stars were even more massive than we thought, creating larger seed black holes that could grow more rapidly. These early black holes weren't just cosmic vacuum cleaners, passively absorbing matter that wandered too close. They were active, dynamic objects that shaped their environments in profound ways. As matter spiraled into them, it formed accretion disks that heated to millions of degrees, glowing brilliantly in X-rays and ultraviolet light. Jets of material shot out from the poles of these spinning black holes at nearly the speed of light, carrying energy and momentum far into the surrounding space. This feedback process had dramatic effects on star formation in the early universe. The intense radiation from actively feeding black holes could heat surrounding gas clouds, preventing them from cooling and collapsing to form new stars. Conversely, the shock waves from black hole jets could compress gas in other regions, triggering bursts of star formation. The interplay between black holes and star formation became a cosmic dance that would continue for billions of years. As the first galaxies took shape, they weren't the elegant spiral structures we see in the modern universe. They were chaotic, irregular objects, constantly merging and disrupting each other as they grew. The cosmic web was denser then, and galaxy collisions were far more frequent. Each merger brought together gas, stars, and supermassive black holes, creating brilliant displays of star formation and black hole activity that could be seen across vast distances. The universe during this era was a much more violent and energetic place than it is today. The rate of star formation was perhaps 10 times higher than in the modern cosmos. Supernova explosions were correspondingly more frequent, filling space with high-energy radiation and heavy elements. The intergalactic medium, the thin gas that fills the space between galaxies, was heated to millions of degrees by the combined effects of stellar explosions and black hole activity. This cosmic violence had an unexpected consequence. The energetic processes in early galaxies began to reionize the hydrogen atoms that had formed during recombination. The universe, which had become neutral and transparent 300,000 years after the Big Bang, began to turn back into a plasma. But this time, instead of being opaque, the ionized gas remained largely transparent because it was much less dense than it had been in the early universe. The epoch of reionization, as astronomers call this period, fundamentally changed the character of the cosmos. It marked the end of the Dark Ages and the beginning of the modern era of cosmic evolution. The universe became transparent to most wavelengths of light, allowing us to observe distant galaxies and study cosmic history. Without reionization, the universe would have remained largely opaque to optical and ultraviolet light, making much of modern astronomy impossible. But reionization wasn't a sudden event. It happened gradually over hundreds of millions of years, with different regions of space being ionized at different times. Islands of ionized gas around the brightest early galaxies gradually expanded and merged until eventually the entire universe was reionized. This process left subtle imprints in the cosmic microwave background radiation that we can still detect today, providing another window into the universe's early history. As the first billion years of cosmic history drew to a close, the universe had transformed from a dark, quiet place into a bustling metropolis of galaxies and black holes and newborn stars. The cosmic web had taken on its basic structure, with matter concentrated in filaments and nodes while vast voids expanded between them. The first heavy elements had been dispersed throughout space, setting the stage for the formation of rocky planets and the emergence of complex chemistry. But the universe was still young, still in its adolescent phase. Most of the stars that would ever form had yet to be born. Most of the galaxies we see today were still assembling from smaller fragments. The supermassive black holes that would eventually regulate star formation in massive galaxies were still growing toward their eventual enormous sizes. Dark energy, that mysterious force that drives the accelerated expansion of space itself, was beginning to dominate over matter and radiation. The universe had been decelerating its expansion for the first several billion years as gravity fought against the initial impetus of the Big Bang. But around 5 billion years after the beginning, dark energy began to win this cosmic tug-of-war, and the expansion started to accelerate again. This transition from deceleration to acceleration marked another phase change in cosmic evolution. It meant that the universe would continue expanding forever, that galaxies would eventually become isolated islands in an increasingly empty cosmos. But it also meant that there was still time for remarkable things to happen, for stars to form and planets to coalesce and life to emerge and evolve and develop the capacity to understand its own cosmic context. The story of the universe's first billion years is really the story of how simplicity gave birth to complexity, how the smooth, uniform cosmos of the early moments after the Big Bang developed the rich structure we observe today. It's a tale of phase transitions and feedback loops, of how small differences amplified into vast cosmic structures, of how the interplay between matter, energy, space, and time created the conditions for everything that would follow. Tonight, as photons from these ancient galaxies continue their journey across expanding space toward Earth, some of them are entering our telescopes and detectors, carrying information about processes that happened when the universe was just a fraction of its current age. These ancient messengers of light have traveled for over 13 billion years to reach us, and in their spectral signatures, we can read the chemical composition of stars that died before our solar system was even born. We are archaeologists of light, digging through layers of cosmic time to understand how the universe evolved from its simple beginnings into the complex, beautiful, mysterious place we find ourselves in today. Each observation adds another piece to the puzzle, but also reveals new depths of complexity, new questions to explore, new wonders to contemplate as we drift towards sleep under the same stars that have been shining down on countless worlds for billions of years. The universe was entering what astronomers now call the Age of Assembly, a period when cosmic evolution shifted from the dramatic fireworks of the first stars to the more patient work of building the structures we recognize today. Gravity continued its steady labor, but now it had better tools to work with. The heavy elements scattered by dying stars began to change everything about how new generations of celestial objects could form and evolve. These second-generation stars were fundamentally different from their ancient predecessors. Where the first stars had been limited to hydrogen and helium, these newcomers incorporated carbon, oxygen, silicon, iron, and dozens of other elements into their composition. This cosmic enrichment allowed them to burn more efficiently, to live longer, to die more gently. Some of these stars would survive for 10 billion years or more, providing the steady, reliable energy sources that complex processes would eventually require. Around these longer-lived stars, something unprecedented began happening in the swirling disks of gas and dust left over from their formation. The heavy elements didn't just float freely in space, they began to condense, to stick together, to form the first solid particles the universe had ever known. Tiny grains of silicon and oxygen combined into microscopic crystals. Iron atoms clustered into metallic specks no bigger than smoke particles. Carbon began its long journey toward the complex molecular architectures that would one day animate living things. These dust grains danced in vast spirals around their parent stars, carried by stellar winds and radiation pressure, but also drawn together by their own faint gravitational attraction. Over millions of years, electrostatic forces caused grain to stick to grain, building up larger and larger aggregates. What started as cosmic dust became pebbles. Pebbles became boulders. Boulders became asteroids. And asteroids began the slow process of sweeping up their neighborhoods to become worlds. The formation of the first planets marked another profound phase transition in cosmic evolution. For the first time since the Big Bang itself, the universe had created objects with solid surfaces, with distinct boundaries between inside and outside, with the potential for complex chemistry to unfold in stable environments. These early worlds were harsh places, bombarded constantly by leftover debris from their formation, their atmospheres stripped away and reformed multiple times by the violence of the young solar systems they inhabited. But some planets formed in just the right locations around their stars, neither too hot nor too cold, in what astronomers call the habitable zone. On these worlds, if they managed to retain atmospheres and develop stable climates, liquid water could exist on their surfaces. And wherever liquid water persisted for extended periods, chemistry began to explore possibilities that had never existed before in the cosmos. The transition from geochemistry to biochemistry represents perhaps the most mysterious chapter in the universe's story. Somewhere, somehow, in tide pools, or deep ocean vents, or shallow lakes on worlds we may never identify, molecules learn to copy themselves. Simple chemical reactions became self-perpetuating cycles. Information began to be stored, not in the quantum fluctuations of empty space, or the nuclear arrangements of atoms, but in the sequences of molecular building blocks that could be copied, modified, and passed on to future generations. This emergence of life was almost certainly not a single event, but a gradual process that unfolded over hundreds of millions of years. Self-replicating molecules became enclosed in protective membranes. Metabolism emerged as these early life forms learned to harvest energy from their environments. The first primitive cells divided and multiplied, each generation slightly different from the last, exploring the vast space of possible biological solutions to the challenges of existence. Meanwhile, on the largest scales imaginable, the cosmic web continued its own evolution. The filaments of dark matter that connected galaxy clusters became highways for the flow of ordinary matter. Gas streams flowed along these cosmic arteries like rivers of hydrogen and helium, feeding the continued growth of galaxies and providing raw material for ongoing star formation. The universe was developing a circulatory system, a way of transporting matter and energy from regions of abundance to regions of scarcity. Dark energy, that enigmatic force driving the accelerated expansion of space itself, was beginning to reshape the fundamental geometry of the cosmos. Measurements from distant supernovae in the late 1990s revealed that the universe's expansion wasn't slowing down as everyone had expected, but actually speeding up. This discovery came as a complete shock to cosmologists and earned its discoverers a Nobel Prize. But it also opened up profound new questions about the nature of space and time and energy. Recent observations suggest that dark energy might not be the constant force we initially thought it was. There are hints that its strength may be changing over cosmic time, weakening or strengthening in ways that could dramatically alter the universe's ultimate fate. Some measurements indicate that the expansion rate of space is accelerating faster now than it was in the past, while others suggest subtle variations that don't match our current theoretical models. These discoveries highlight just how much mystery still surrounds the fundamental nature of our cosmos. Dark matter and dark energy together make up roughly 95% of the universe, yet we understand almost nothing about what they actually are. We know they exist because of their gravitational effects, because of the way they shape cosmic structure and drive cosmic expansion, but their fundamental properties remain completely enigmatic. This might seem frustrating, but it's actually cause for profound excitement. We live at a moment in cosmic history when the universe is still revealing its deepest secrets, when each new observation has the potential to revolutionize our understanding of everything. The James Webb Space Telescope continues to surprise us with images of galaxies that formed earlier and grew more massive than our theories predicted. Gravitational wave detectors are opening entirely new windows on cosmic evolution, allowing us to study the collisions of black holes and neutron stars in ways that would have seemed like science fiction just a few decades ago. Underground laboratories search for the elusive particles of dark matter, hoping to finally identify the mysterious substance that provides the scaffolding for all cosmic structure. Space-based observatories map the cosmic microwave background with ever-increasing precision, revealing subtle patterns that carry information about processes that happened in the first fraction of a second after the Big Bang. Neutrino detectors buried deep beneath mountains and oceans catch ghostly particles that stream directly from the hearts of stars and supernova, carrying information about the most extreme environments in the universe. Each of these observational techniques provides a different perspective on cosmic evolution, like viewing a vast landscape from multiple vantage points. When we combine all these different ways of studying the universe, a remarkably consistent picture emerges, but one that's also full of surprises and contradictions that point toward new physics waiting to be discovered. The cosmic microwave background radiation continues to be refined by increasingly sensitive instruments, revealing ever more subtle temperature fluctuations that carry the fossil imprints of quantum processes from the inflationary epoch. These observations have confirmed many predictions of Big Bang cosmology with extraordinary precision, measuring the universe's age, composition, and geometry to accuracy levels that would have seemed impossible just a generation ago. But these same precise measurements have also revealed tensions and inconsistencies that suggest our understanding is still incomplete. Different methods of measuring the universe's expansion rate give slightly different answers, a discrepancy known as the Hubble tension that could be pointing toward new physics operating on cosmic scales. The way matter clusters on large scales doesn't perfectly match what we'd expect from our models of dark matter and dark energy, hinting at possible modifications to our theories of gravity or new interactions we haven't yet discovered. Some of the most intriguing puzzles come from studies of the universe's earliest galaxies. How did supermassive black holes grow so massive so quickly in the cosmic dawn? How did the first galaxies assemble their stars so efficiently? Why do some of the most distant observable galaxies appear brighter and more organized than our evolutionary models predict? each question opens new avenues for investigation, new possibilities for discoveries that could reshape our understanding of how cosmic structure develops over time. The search for life beyond Earth has become deeply intertwined with our understanding of cosmic evolution. We now know that planets are common around other stars, with most Sun-like stars hosting at least one world in their habitable zones. Organic molecules exist throughout interstellar space. The building blocks of life are present in meteorites and comets, and the chemical elements essential for biology have been distributed throughout the cosmos by generations of dying stars. The question is no longer whether the conditions for life exist elsewhere, but how commonly those conditions actually give rise to living systems, and how often life develops the complexity and intelligence necessary to contemplate its own cosmic origins. Are we rare products of an unlikely series of evolutionary accidents, or inevitable outcomes of processes that unfold wherever the right conditions persist for sufficient time? As we probe deeper into these fundamental questions, we're also developing new ways to observe and understand the universe around us. Machine learning algorithms help us identify subtle patterns in vast astronomical datasets. Quantum sensors promise unprecedented precision in detecting gravitational waves and other cosmic phenomena. Advances in materials science and engineering are enabling the construction of telescopes and detectors that would have been inconceivable just a few years ago. The story we're constructing about cosmic origins grows richer and more nuanced with each passing year. We've learned that the universe is far stranger and more beautiful than anyone could have imagined when cosmology was just beginning to emerge as a scientific discipline. It's a place where space itself can expand faster than light, where quantum fluctuations can grow into galaxies, where the vacuum seethes with virtual particles, where black holes can merge and send ripples through the very fabric of space-time. Yet for all its strangeness, the cosmos follows deep mathematical principles that human minds can discover and understand. The same physical laws that govern the behavior of atoms in our bodies also determine the evolution of stars and galaxies. The same quantum mechanics that makes modern technology possible also shaped the primordial density fluctuations that became the cosmic web. There's a profound unity underlying all this apparent complexity, a set of fundamental relationships that connect the smallest scales to the largest. This unity suggests something remarkable about the nature of existence itself. We're not accidental observers looking in from the outside at a universe that has nothing to do with us. We're integral participants in a cosmic story that has been unfolding for nearly 14 billion years. Temporary arrangements of ancient stardust that have somehow developed the capacity to understand our own origins and contemplate our place in the vast scheme of things. The atoms in your brain were forged in the nuclear furnaces of dying stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created through processes of stellar evolution that played out over billions of years before our solar system even existed. You are literally made of star stuff, assembled through an unbroken chain of cosmic processes stretching back to the Big Bang itself. But you're more than just a collection of recycled stellar material. You represent something genuinely new in the universe's history, as far as we know. For the first time, matter has organized itself in such a way that it can contemplate its own existence, can feel wonder at the beauty and complexity of the cosmos, can ask questions about meaning and purpose, and the ultimate fate of everything that exists. Human consciousness might be commonplace throughout the universe, arising naturally wherever conditions allow for sufficient biological complexity. Or it might be vanishingly rare, a cosmic accident so unlikely that we may be alone among the stars. Either possibility is profound in its own way. Either scenario imbues our existence with a significance that transcends our brief individual lives. Tonight, as you rest beneath the same sky that has witnessed the entire sweep of cosmic history, you're surrounded by invisible reminders of this vast story. Cosmic ray particles created in distant supernovae pass through your body every second. The cosmic microwave background radiation bathes you in the afterglow of the universe's birth. Neutrinos from nuclear reactions in the sun's core stream through you by the billions, most of them passing through the entire Earth without interacting with a single atom. The darkness above you isn't empty, but filled with galaxies beyond counting, each containing hundreds of billions of stars. Many of those stars likely surrounded by planets where the same fundamental processes that led to life on Earth may be playing out in countless variations. The universe that began with nothing has become everything we can observe, and much more that remains hidden from our current instruments and theories. As sleep approaches and consciousness fades into dreams, remember that you are the cosmos becoming aware of itself through the temporary arrangement of particles that constitutes your body and mind. The story that started with quantum fluctuations in the primordial void has led, through an almost unimaginably complex series of events, to this moment of awareness, this capacity to wonder at the mystery and beauty of existence itself. In the depths of space between the galaxies we can see and the dark matter we cannot, something else stirs in the cosmic darkness. Scientists have recently begun to suspect that the very fabric of space-time itself may be more dynamic, more alive than we ever imagined. The vacuum of space, which appears empty to our instruments, may actually be seething with activity at scales so small we can barely conceive of them. Quantum field theory tells us that even in the most perfect vacuum achievable, virtual particles are constantly popping into existence and annihilating each other in timeframes so brief they exist only as mathematical possibilities. But these quantum fluctuations may have left their mark on the universe in ways we're only beginning to understand. They may be responsible for more than just the initial seeds of cosmic structure. They may be actively shaping the evolution of space and time even now. Recent experiments in laboratories around the world have begun to probe these quantum effects with unprecedented precision. Researchers have detected subtle changes in the behavior of light as it passes through regions of space where these virtual particles should be most active. Others have measured minute distortions in the fabric of space-time itself, ripples so small they stretch and compress distances by less than 1,000th the width of a proton. These observations are forcing physicists to reconsider some of their most fundamental assumptions about the nature of reality. The boundary between something and nothing, between matter and vacuum, between existence and non-existence, may be far more fluid than we realized. The universe may be continuously creating and destroying itself at the quantum level, a process of constant renewal that has been going on since the first moment of the Big Bang. This quantum creativity may help explain one of the most puzzling aspects of cosmic evolution: how complexity continues to emerge from simplicity even as the universe expands and cools. Entropy, the tendency toward disorder, should gradually smooth out all structure, leaving behind a cold, uniform cosmos devoid of stars, planets, or life. Yet somehow, local pockets of order continue to form and flourish, defying this universal trend toward equilibrium. The answer may lie in the relationship between information and energy at the quantum scale. Every time a quantum measurement occurs, every time a particle's position or momentum becomes defined, information is created. This information has to go somewhere, and its storage and processing may require the expenditure of energy in ways that actually increase local order while contributing to global entropy. Life itself may be one manifestation of this process. Living systems are extraordinarily efficient at capturing and organizing information, at building complex structures that can maintain themselves against the forces of decay and dissolution. From this perspective, the emergence of life wasn't an accident, but an inevitable consequence of the universe's fundamental tendency to explore all possible ways of organizing matter and energy. But biological evolution represents only one pathway among many that the universe has discovered for creating complexity. On scales vastly larger than living organisms, galaxies themselves exhibit behaviors that seem almost organic. They grow by consuming smaller neighbors. They reproduce through collisions that trigger bursts of star formation. They adapt to changing environments as dark energy alters the cosmic expansion rate. Some astronomers have begun to wonder whether galaxies might possess a primitive form of information processing, a way of responding to their environments that goes beyond simple gravitational attraction and repulsion. The supermassive black holes at galactic centers might serve as computational cores, processing information about matter and energy flows throughout their host galaxies and adjusting their activity accordingly. These ideas push at the boundaries of scientific respectability, venturing into territories where physics meets philosophy and objective observation blends with speculative interpretation. But they reflect a growing recognition that the universe may be far more strange and wonderful than even our most advanced theories suggest. The James Webb Space Telescope continues to challenge our assumptions with each new observation. Galaxies that formed in the cosmic dawn don't just appear earlier and grow faster than expected. They exhibit organizational principles that seem to violate everything we thought we knew about how structure assembles in the young universe. Some appear to have formed their stars in coordinated bursts that span hundreds of thousands of light years, as if following some kind of cosmic choreography. Other observations reveal structures that shouldn't exist according to our current models. Vast streams of galaxies flowing in coordinated patterns across hundreds of millions of light years. Alignments of galactic rotation axes that extend across cosmic scales where no physical mechanism should be able to maintain such organization. Correlations between the properties of galaxies and the large-scale structure of the cosmic web that suggest information can somehow propagate faster than light across intergalactic distances. Each of these discoveries forces astronomers to consider possibilities that would have seemed absurd just a few years ago. Perhaps the cosmic web itself possesses emergent properties that arise from the collective behavior of dark matter particles. Perhaps information can be encoded in the quantum structure of space-time in ways that allow distant regions of the universe to remain correlated long after they've lost causal contact. Or perhaps our entire framework for understanding cosmic evolution needs to be reconsidered from the ground up. Some theorists have begun to explore the possibility that what we call the Big Bang wasn't actually a beginning, but a transition, a moment when our observable universe budded off from some larger, more complex structure that we can never directly observe. In these models, the apparent fine-tuning of physical constants that allow stars and planets and life to exist isn't a remarkable coincidence, but an inevitable consequence of a selection process operating at scales beyond our current comprehension. Our universe may be just one bubble in an infinite foam of space-time, each bubble with slightly different physical laws, most of them sterile and lifeless, but a few, like ours, capable of supporting the emergence of complexity and consciousness. The implications are staggering. If this multiverse hypothesis is correct, then everything we can observe, from the smallest quantum fluctuation to the largest galactic supercluster, represents just one example of what's possible when the fundamental forces and particles combine in particular ways. Somewhere in this infinite ensemble of possibilities, every conceivable variation of physical law and cosmic history plays out. But even if our universe is unique, even if we represent the only arrangement of matter and energy that has ever achieved self-awareness, the story of cosmic evolution remains profound beyond measure. The fact that quantum fluctuations in the primordial vacuum could grow into galaxies and stars and planets and life and consciousness speaks to deep principles of organization and creativity that seem to be built into the very foundation of existence. Modern cosmology has revealed that we live in a universe that's not just expanding, but accelerating its expansion, driven by dark energy, whose nature remains completely mysterious. This acceleration means that in the far future, galaxies beyond our local group will disappear beyond the cosmic horizon, their light redshifted into undetectability. Future civilizations, if any arise, may find themselves in a universe that appears static and eternal, with no evidence of the Big Bang or cosmic evolution. But even in that distant future, when the last stars have burned out and black holes have evaporated through Hawking radiation, the quantum vacuum may continue its creative work. Virtual particles will still flicker in and out of existence. Quantum tunneling may still allow for rare but spectacular events, the spontaneous formation of new universes, or the resurrection of complexity from apparent emptiness. The universe that began with nothing may return to nothing, but that nothing will still contain within it the potential for everything. The same quantum principles that gave birth to our cosmos will persist, ready to create new realities from the void whenever the right conditions arise. In this sense, the story of cosmic evolution has no true ending, only endless transformations from one state of being to another. Tonight, as you lie suspended between waking and sleeping, you're participating in one of those transformations. Your consciousness is preparing to dissolve temporarily into the quantum uncertainty of dreams, where the normal rules of logic and causality break down and new possibilities emerge. In sleep, your brain recreates the conditions of cosmic creativity, allowing random neural fluctuations to combine and recombine into novel patterns of thought and imagination. The boundary between your inner universe of mind and the outer universe of stars and galaxies grows thin in these twilight moments. The same fundamental processes that gave birth to cosmic structure billions of years ago continue to operate in the electrochemical networks of your nervous system. Your thoughts and dreams are made of the same quantum stuff as the cosmic microwave background, organized by the same principles of information processing that govern the evolution of galaxies. As consciousness fades and the familiar world dissolves into the strange logic of sleep, remember that you are both observer and participant in the greatest story ever told. The universe that emerged from quantum nothingness has somehow organized itself in such a way that it can contemplate its own existence through minds like yours. Every dream you dream, every thought you think, every moment of awareness you experience adds another page to the ongoing narrative of cosmic evolution. The darkness that surrounds you isn't empty, but filled with invisible processes of creation and destruction, with quantum fluctuations that may be seeding new universes even as you drift towards sleep. You are the universe dreaming about itself, a temporary arrangement of stardust that has learned to wonder at the mystery of existence itself. Rest now in the knowledge that your brief moment of consciousness is part of something infinitely larger and more beautiful than any individual mind can fully grasp. The story continues, has always been continuing, will always continue, in forms we can barely imagine, and through transformations that stretch the very meaning of existence itself. And so we reach the end of our journey through cosmic time, though of course there is no true end to this story. We've traveled from the quantum nothingness that preceded existence itself to the vast, expanding cosmos we inhabit today. We've watched as space and time emerged from a singularity smaller than an atom, witnessed the first light piercing the cosmic fog, seen the birth and death of primordial giants that forged the elements in our very bodies. Every breath you take connects you to that ancient story. Every atom in your flesh was once part of a star that burned billions of years ago. You are not separate from this cosmic narrative, but woven into its very fabric, a temporary arrangement of stardust that has somehow learned to contemplate its own origins. The universe began with nothing and became everything, including you, in your thoughts, in your dreams, in this very moment of quiet reflection. The cosmos has found a way to know itself. That may be the most extraordinary chapter of all in this ongoing story of creation. Sleep well, knowing you carry within you the memory of 13 billion years of cosmic evolution. Tomorrow the story continues, as it always will, in ways we can barely begin to imagine.